be doing these kind of seminars or webinars more often than what we're doing now. So that's a good development, I think. Also, I'd like to acknowledge Dr. Pandey in the audience, as well as Dr. Mahadevan. Of course, Ashutosh just joined, I guess, from LRD, and also Devdeep. Thanks for joining for the session here. With that, let me share my screen and go ahead with the presentation. And I think I had to let me stop. I guess I need to do something because I have a short video I want to show. I think I need to do something to show the video or have the audio come through. Okay. As it would happen, I guess something happened on my screen. I don't no longer see. Yeah, I see. See the content. Okay, got it. Okay, so are you able to see my screen?
Yes, sir, it's coming up.
Good. Hope it is come out.
Yes, yes.
Very good. Thank you very much. Of course, today, it's a series of webinars that we are presenting for this workshop. Let me turn off my video if I can. Apparently, I can't. Okay, that's okay. I guess you get to see me for the next 1 hour. So I think we'll start with, I think we have a series of talks, I guess, this week, excellent talks by Soundarya as well as Karthik later on this week. Because today I'll focus more on computational electromagnetic techniques for the antenna designs. Because more than often what happens is that most of us are using simulation tools, but of course simulation tools are what they call the tools, right? Ultimately, we have to do the design. We have to know what is behind the tools and how to use the tools when appropriately possible. So that's what my talk will be today. For those of you who are not familiar with Altair, I'm going to introduce a couple of slides on Altair itself. And then we'll go into how the antenna analysis is normally done and talk about the computational electromagnetics and more detail into full wave solutions, asymptotic solutions, and hybrid solutions. Then briefly touch on antenna arrays, both infinite and finite. I'm not going to talk too much about it because tomorrow Soundarya is going to do an hour-long session on arrays. Then also touch on the advanced topics like characteristic mode analysis, machine learning for antenna design and optimization. Again, I won't go into the deep because they themselves are more than an hour or 2 hour presentations. Then talk about antenna modeling and simulation education and provide some further reading materials for that. With that, let me start with a short video. This is, though it's an Altair video, it kind of shows where the world is heading in terms of the simulations wise. So in the past, it used to be Excel sheets and those kind of things. Then very, what I call segmented simulations for antennas and mechanical and those kind of things. Now the whole thing is coming together with simulations for electromagnetics are also combined with mechanical analysis, but also combined with data analytics and Internet of Things and everything. So that's where, of course, our company is focused as well. So the video will be somewhat of, what's happening in today's simulation world. So let me play the video.
The world is facing big changes, challenging companies to evolve in faster and more radical ways. At Altair, We're helping lead the global evolution toward a smarter, more connected world, integrating electronics and controls with mechanical design to expand product value, developing AI, simulation, and data-driven digital twins to drive better decisions, and delivering advanced HPC and cloud solutions to support massive idea exploration. To set the pace of innovation, not just keep step with the pack, we must look beyond the horizon to embrace the explorer in each of us. Imagine being free to follow your inspirations and ideas wherever they lead, to experiment and propel unbounded discovery, to dream, innovate, and solve in ways that move us all forward. Our solutions are forged in analysis and technology, and shaped by humanity and creativity, the spirit that keeps our minds open for a constant forward vision. We are determined to share our thirst for limitless exploration, to empower progress, and free our clients to deliver next-generation products. Explore the world with us and go beyond. Ready to go? Altair. Only forward.
Okay, with that, of course, Altair started in 1985 as a very small company. Actually, 3 people started the company in Troy, Michigan, but now we can see that it has grown into $500 million revenue in 2019 with 3,000 employees all over the world, actually more than that by now, and 86 offices in 25 countries. So, of course, this is also a message for the younger engineers and entrepreneurs that when you start small, you don't have to think that we can't do big things. Altair is actually an example of how we can start small and can grow to a multinational company in the long run. Also, Altair has a very big presence in India, not only in the sales and marketing, but also in the development side. So we have one of the largest offices in Bangalore, based there. And then we have offices in Pune, Delhi, Chennai, and Hyderabad, and other places as well. So we serve the Indian market and also the subcontinent there very well from our Bangalore office. We have around 11,000 customers all over the place. Actually, this is an old number. I'm sure every year it's growing. You can see that what's amazing here is the verticals we have: automotive, aerospace, of course, that can be expected; education, obviously, very important for us; energy, financial sectors. This is actually coming through the data analytics side of our business. Government and defense, heavy rail, heavy train systems as well, industrial goods. So any industry you can think of, we have our footprint there. So why is that was possible? Because of the fact of the broad solutions portfolio we have in modeling and design, modeling and visualization, and also multiphysics simulation. Any physics you can think of, we have simulation tools in that. Of course, the latest one that we added was machine learning and data analytics, which is becoming a huge thing for the predictive analytics in terms of failure-wise. Probably some of you might have heard yesterday, or maybe day before yesterday, there was a kind of an accident. It did not result in any big thing. The United Airlines flight that is flying from Denver going to Honolulu, the engine caught fire, but they could turn around and go back. So those are the failures that one would predict ahead of time. If one could predict ahead of time, you could prevent those kind of things. Machine learning, data analytics can help do those kind of things, and we are actually working with those big companies to implement some of those things, of course, through Internet of Things, high performance cloud computing. Of course, we have partnered with other companies as well. So in terms of multiphysics optimization, we cover a whole range of physics. For example, system simulations, that's 1D, manufacturing simulation, that extrusions and molding and those kind of things. Electromagnetics, obviously, that one talk we're going to have today, and structural analysis, crash and safety, thermal and fluid dynamics, all of them combined with optimization enabled solutions, meaning not only that, but now, of course, we're also going to more towards machine learning optimization, not just a simple optimization, machine learning optimization for all our solutions. So now let's get to the topic of today, that's antenna analysis. Of course, antennas obviously follow the Maxwell's equations. Actually, Maxwell put together these 4 equations as a compilation of various laws that govern electrical phenomena, the electric fields and magnetic fields. And they're actually called second great unification in physics after the Newton's laws for gravity and those kind of things. So we can think of Maxwell as the father of electromagnetics. Then came a little bit of a practical application by Marconi, with the invention of radio. And of course, he has done an experiment in 1901, sending signal from England to Canada, almost like 2,200 miles or 3,500 kilometers wirelessly. And of course, he has been very entrepreneurial. So he started a company called Marconi's Wireless Telegraph Company of Canada in 1903. Until recently, it has been in business. It's called Canadian Marconi Company, and then it was renamed later as CMC Electronics. Now, why I know this name is because they've been using our software for some time. If I'm correct, I guess they may still be using. And of course, later they were acquired by a company called Esterline Corporation. It's good to see the company that started in 1903 still in existence and doing these kind of things. That shows the persistence of electromagnetics and antenna technology over the years. Of course, not to forget our own Sir Jagdish Chandra Bose, who actually did this is actually documented that his experiment on millimeter waves was preceded even before Marconi's experiment. In 1894, he demonstrated ringing of a bell wirelessly by generating the millimeter wave signals through ignition of the gunpowder. Of course, he wrote that the invisible light, of course, that's an electromagnetic signal, can easily pass through brick walls, buildings. Therefore, the messages can be transmitted by means of it without the mediation of wires. Of course, that's what we're living through now after so many years, maybe more than 100 years. Of course, in 15th of September 2012, IEEE declared a milestone in electrical and computer engineering about the Bose's experimental work. There's a link, I guess, where you can read the more details. So from those humble beginnings, I guess antennas now come to be everywhere in the industry. That is, you take any industry, automotive, aerospace, defense, communications, consumer electronics, energy, healthcare. Of course, with the Internet of Things, there is no product that doesn't come with an antenna because every product is now connected with a Bluetooth and a Wi-Fi connection. So everything needs to have an antenna to communicate through those kind of protocols. That also makes it very critical that we educate our students in good antenna theory and good background in simulation technology, so they can be very productive and also produce innovative products for many years to come. So analyzing antennas means solving Maxwell's equations because they follow the Maxwell's equations. So in terms of electric and magnetic field, and as well as electric current and magnetic current. So again, going back to Maxwell's equations, when you solve them in terms of vector potentials as well as the currents and those kind of things and Green's function. So basically, you solve for electric field, and of course, electric field, the vector potential can be written in terms of Green's function multiplied by the current or the volume of the surface of the electric current. Of course, this is a free space Green's function that can be written this way. So in addition to that, you also have to satisfy the boundary conditions at every interface of the medium. For example, medium 1 is this one and medium 2 is this. At the interface of the medium, you have to have boundary conditions. One is the tangential electric field is continuous across this boundary. If it's a conducting surface, perfectly conducting surface, then it is 0 at the surface. Same thing with the magnetic field is discontinuous across the interface up to the point that to the surface current there. So if you take H2 minus H1 equals J on the surface, if it's a magnetic, if it's a conducting surface, of course, then you satisfy both the electric and magnetic fields at the surface. So with that, if you want to solve any antenna problem, let's take a dipole which is excited in the middle here. You can write the vector potential that I talked about as integration of the over the contour, because it's a straight line here. The current and the free space Green's function e to the power minus jkr by r multiplied by dl dash. That is the integration here. Looks very simple. The key thing is the current distribution on the dipole. So if the dipole, this length is very, very small, let's say it's lambda by 50, then it's a constant current, so it becomes very easy to integrate this integral here. If it becomes slightly longer, up to lambda by 10, you can think of the current varying linearly. Your vector potential gets a little bit more complex, I would say. Then, of course, if it becomes greater than lambda by 10, the current varies sinusoidally. It gets even more complicated. Obviously, most of you who went through the basic antenna classes would have solved this equation and got the current distribution to be sinusoidal and then the directivity, etc., which is good. But if you were to do the simulation of the same thing, all you would do is you construct the dipole geometry, and then you provide the excitation, you request the fields, then you can compute the near fields and far fields, as well as the current distribution there. So, but with the simulation, you don't have to stop there, because you don't have to solve any equation here. Now you can actually use surrounding environment. For example, you can put a cylinder, you can put a sphere, for that matter, dielectric sphere here, and compute the fields. So the point I'm driving across is that if you were to analytically derive these equations, they could get more and more complicated when you add more and more objects to it. And of course, with the simulations, you can play around with them. Doesn't matter if it's a cylinder, sphere, or any other structure, you can place it and you will be able to solve it. How do we do that? That is using computational electromagnetics. So what that means is that if we have a physical structures, like anything, like cell phones, ships, or any type of antennas, obviously you have to solve Maxwell's equation. There is no magic here. We're still solving Maxwell's equations, but in a different way than writing the equations the way we wrote before for a particular structure. So essentially, you discretize these structures, the physical structures. So each discretization part where you can impose your boundary conditions, that electric and magnetic fields, so that you'll be able to solve for those quantities, and then of course add them up over the object, so you can have the currents, the fields, anything you like to have for an antenna available to you. So just as an example, I guess if you take an aircraft like this one, for example, you make a CAD model of that. There is a small antenna on the top. These are typically the blade antennas they put on the top for ground communications. Then you discretize it. That is, make that into small parts. If you look closely, they are the triangles, and you solve for the Maxwell's equations on each triangle. When I say we, I guess this is what the computer simulation tool that you use is doing it. It is solving the Maxwell's equations on this triangle, and then adding up all those triangles together to give you the currents on the structure. Also from the currents, by integrating the currents, you can find the radiation pattern. One key thing to remember, I guess, is the size of this triangle. The size of the triangle is dependent on the wavelength. So typically what that also means, sampling of the current, right, with respect to the wavelength. So if you have a sinusoidal wave, how many points you want to put on a sinusoidal wave to discretize it to represent a good sinusoidal wave. So in that same respect, if you can say 10 points is good enough. Typically, the size of the triangle is lambda by 10. Of course, it can be more or less depending on how the current is varying on those structures. Now, of course, we have done this with the discretization. It doesn't matter which object you bring into the simulation. For example, you bring in a car with a shark fin on the top, you can discretize it. You can find the currents, you can find the radiation pattern. You can bring a ship with a little monocone antenna on the top, even including the little some surface of the sea, and you can discretize it, and you can find the currents, you can find the radiation patterns. In that respect, we have solutions. Obviously, our software tool is called FEKO, which can solve any type of antenna design problem. But we also introduced a propagation tool called WinProp, which can take the inputs from FEKO as the radiation patterns and use them as sources for broader propagation analysis. Of course, you can find more information at our website. So how do these things can help together? For example, if you're doing an antenna design, let's say blade antenna, you can design that with a simulation tool. And of course, the blade antenna by itself can have a nice pattern here, but now you want to put that in a helicopter, in the back of the helicopter, for example, the pattern changes. So this is what simulation tool bring to the table. What not only the antenna design, but also what happens in the operating environment to its radiation pattern and its characteristics. Same thing with the, of course, with the WinProp, you can take this pattern here and do a virtual flight test in a city environment as shown here. Same thing in the wireless side, we can simulate the mobile device base station, and then you use the base station and the mobile device in an environment in the city, and then compute the connectivity. Same thing with the Wi-Fi router, etc. here. So coming to the CM solver technologies, we can divide them into two types. One we call full wave solutions, other we call asymptotic solutions. Full wave solutions, fall under so many different methodologies. What these things are, we solve Maxwell's equations accurately. So if your mesh and CAD model is accurate, you should be able to very good solutions, accurate solutions by applying, let's say, method of moments, adaptive cross approximation, multi-level fast multiple method, finite element method, finite difference, time domain. Asymptotic methods also solve Maxwell's equations, but they solve them with some assumptions and approximations. So if the problem fits in those assumptions and approximations, these methodologies also will give you very nice solutions. That is physical optics, large element physical optics, ray launching geometrical optics. Sometimes they call it shooting and bouncing ray method, uniform theory of diffraction. So then, of course, you can use them separately, but also you'd want to be able to combine them in one problem. Let's say you have a large aircraft where you want to place an antenna. The antenna should be able to be, all the details should be able to be modeled, let's say with method of moments or MLFMM. And the aircraft can be modeled with physical optics because it's a smooth surface and large one and can fit well with, let's say, physical optics approximation. So that's, of course, the advantage is that you can combine 2 or 3 different methods to be able to do a complete problem where part of the problem can be done with asymptotic solution like physical optics or ray launching geometrical optics or UTD, and the more detailed part, smaller part, can be analyzed with the full wave solutions like FEM or method of moments and so on and so forth. So this brings the advantage of both methodologies into to picture. So this actual graph shows you the way these methodologies can be used. For example, full wave solutions from FEM, FTTD, method of moments, ACA, and MLFMM. If you look at this chart here, complexity of materials and electrical size, no matter how much memory you have, at some point these methods will run out of memory, and of course time, how much time they take. You may have, let's say, terabyte or even petabyte memory machine, but if they're going to take 1 month, 2 months to solve, that's no good because that's a long time to wait for a solution. But if you want any accurate solution, you start with these full wave solutions first. As long as you have the memory and can afford the time, our recommendation is that you apply the full wave solutions to get the solution. But of course, once you increase the electrical size where you run out of the memory, you can apply physical optics and UTD or ray launching geometrical, because at this point you don't have the memory to solve the problem. Instead of saying I can't solve the problem, at least you are able to get some understanding of the solution and ballpark solution maybe, and in many cases very accurate solutions by doing the asymptotic solutions as well, provided your problem fits into that approximations. Of course, these are all hybridized, as I already mentioned. So that this is where, this is a very powerful way of solving things, but at the same time, if you have to know what you're doing. If you are not sure what you're doing, and you cannot apply brute force simulation to solve problems. So that's why the education behind the simulation technology is very critical in applying the solutions, so simulation solutions effectively. So this actually charts illustrates what these various methods can be applied. For example, if you have wire type of antennas, there's nothing that can beat the method moments and MLFMM in solving them, because I will talk a little bit about the absorbing boundary conditions and all those things. No absorbing boundary conditions. They're all solved in free space very nicely. Of course, if you have planar antennas, then you can have planar Green's function, which is a 2.5D solution. Of course, method moments can also be used, FEM and FTTD. Same thing with arrays. As they get bigger and bigger, you can use MLFMM, FEM, FTTD. Of course, finite array tool that we'll talk a little later on. So on and so forth. Now we can see the picture, I guess. So with the different methodologies that are available, you should be able to solve different types of problems, including the lens antennas here, reflector antennas, as well as mobile and cell phone antennas also. So let's take a look at the full wave solutions to start with. Of course, in the full wave solutions also, we can divide them into two different methodologies. One we call field method, other is called source method. Field method means you discretize the whole volume of your problem space. You have an antenna volume and you discretize it with the tetrahedrals or voxels. So there we solve the differential form of the Maxwell's equations. But you need a special absorbing boundary conditions. Sometimes they call it air box around a radiating structure to be able to simulate that waves are going to infinity. This differential form of solution cannot simulate that, so you have to use this special absorbing boundary conditions. Probably most of you might have used the finite element method and FTTD. They do require this absorbing boundary condition. Means it's a fictitious air box that you put around your antenna to be able to solve the problem. Whereas the source method, it works with the currents and charges, and it is using the integral form of Maxwell's equations. So it uses the surface discretization. So you don't need to discretize the volume. So the wires can be segmented with the wire segments, and the surfaces can be discretized with the triangles. This is an exact treatment of the radiation boundary condition because of the Green's function that we use, similar to what I showed you for the dipole example. So no airbox required. That's one of the big advantages of using these methods. Method moments, ACA, and MLFMM fall in that category. So let's take a look at them briefly on these methods. Method moments, as I mentioned, it's a surface method. So you start with a geometry, for example, a horn antenna here, and you discretize with triangles. And behind the scenes, the method moments forms Zi equals V matrix. That is, Z is the impedance matrix, N by N, that is the N number of unknowns on the surface. I is the unknown vector we want to solve. V is the excitation vector. Of course, as a user of the software, you don't need to worry about it. You just need to know that this is what happens behind the scenes. There is an N by N complex matrix, and there is a V as an excitation vector, and I is the unknown vector that need to be solved. And I can be solved by inverting Z and multiplying with V. And you can get the solution. And once you get the solution, you have the surface currents, you can have the near fields, you have the radiation patterns, and you can have the S parameters, input impedances. Any quantity you want to have, you can have. So typical examples could be, for example, a broadband helix antenna, for example, with curvilinear segments here, discretized with method moments, and you can compute the pattern, and you can also compute the reflection coefficient. But also it can be applied to the dielectric surfaces as well, meaning you don't have to discretize the volume inside the dielectric, you discretize the surface of the dielectric. And this is one example of a coplanar waveguide fed bow tie antenna that is analyzed using method moments solution. So then, of course, this is another example of a patch antenna on a finite ground plane. You have the CAD model, you have the surface mesh, then you can compute the currents, you can compute the radiation pattern, you can compute the 2D patterns as well here. So now we want to take one step further and be able to do a large array on a finite plate like the one we have here. With meta moments, it requires a memory of 125 gigabytes if you want to solve with meta moments. That's because of the number of unknowns. We have 131,000 unknowns. That requires so many complex numbers to be stored because of the matrix. Of course, this I was trying to solve on my own computer, which has only 64 gigabyte of memory. So this you can think of, I hit the wall on the memory side here. So this is where MLFMM comes into picture. Just to explain how MLFMM can help, first we have to see what is the problem with the method moments. In the method moments, remember we talked about this equation where you invert Z and multiply V. This actually takes order of n cube operations to invert this one and order of n square memory to store the matrix. What this means is that in real terms, if you have frequency at, let's say, 1 gigahertz, and you discretize and you're able to solve it, and you want to double the frequency, that means you reduce the mesh size, means your number of unknowns became 4 times because of the surface, because you use 2 sides of the surface. So order of n cube means you increase the runtime by 64 times. That is, instead of 1 hour, now you're running 64 hours. Instead of 1 gigabyte of memory, now we have 16 times the memory, 16 gigabytes of memory. So that's where MLFM comes into picture and makes them to be linearly scaled than n cubed and n squared. That is, the memory only increases by 5 times rather than 16 times, and the runtime increases by approximately 66 times rather than 64 times. So now you can do much larger problems with the same memory and in a lesser time. So if you take the same example that we have taken before, the 106 elements array on a plate, now we are able to solve this problem with 11 gigabytes of memory in 10 minutes. So that's a big jump from a jump down from 125 gigabytes that meta moments required with 11 gigabytes. So you maybe even be able to solve this on a laptop rather than having to go to a bigger computer or a HPC kind of thing. So now we can actually take the whole satellite into account. This is actually a satellite antenna on one surface of the satellite here, one wing of the satellite. You can take the whole satellite CAD model and to be able to analyze. Meta moments would have taken approximately 1 terabytes of memory for this. Of course, this MLFM took still 11 gigabytes because it gets better as the electrical size increases. So the point I'm drawing here is that by brute force solving with meta moments, we would have never solved this problem. By switching to MLFMM, now we are able to solve it with much less memory and affordable time. So similarly, you can apply MLFMM to reflector antennas, as I'm showing here. Obviously, the aperture size dictates the size of this problem. So you can go from, let's say, 19 wavelengths of aperture size to 60 wavelengths. Still, we're talking about only 12 gigabytes of memory with the MLFMM. So coming to finite element method, now we have seen the meta moments MLFMM as the source methods. Now let's take a look at finite element method. As I mentioned before, this is a volumetric discretization or differential form of Maxwell's equation. So you discretize with tetrahedrals. And one advantage with FEM is that it forms a sparse matrix. That means not all elements are populated, so you'll be able to store them efficiently, be able to solve them efficiently. Only disadvantage is that you have to apply this air box around it that needs to be used, because then your problem becomes a little bigger than the actual problem size. This is where the hybridization can help, that FEM method moments. So where, let's say you have a human body with multiple dielectrics, this is where you can apply FEM inside the body. And of course, you can truncate with the method moments or MLFMM you have an antenna close by. If you have to do this purely with FEM, you have to create a big air box and discretize the whole volume. Whereas here, you discretize just the antenna because it's a metallic surface. And then, of course, you discretize the FEM with the meta moments, and then there's no mesh in this white space, which can save a lot of memory and time if you were to study this with a, let's say, increasing distance. So then, the computation cost will not increase with the distance. Of course, you can do patch antenna type of applications, as well as even more complicated ones where we can combine. Let's say this is a circulator here where you're sending the energy in this way. When it is received, it's coming back into the other port here. So here you can apply FEM very well into this one. Here, actually, you don't need the airbox because it's a closed boundary and there's no radiation happening. But here in this portion, you can apply MLFMM where radiation is happening. So you don't have to discretize the volume. And of course, if you have a lens, you can also apply meta moments to it and efficiently solve this problem than applying one method and trying to solve this in a brute force way. Same thing with the finite difference time domain method as well. Only difference between FTTD and FEM is that obviously it's a time domain. That's one difference. Second difference would be you discretize with voxels like these ones. And it takes much less memory because it doesn't form a matrix. One disadvantage is that the mesh of the FTTD, because of the voxels, could be what we call a staircase approximation of the curved surfaces. That one need to keep in mind in applying FTTD. So, the same way as we applied in FEM, you can also solve a patch antenna, typical patch antenna type of problems with FTTD, and you can also see that it needs an airbox like any volumetric methods. So let's move on to the asymptotic and hybrid solutions. The motivation is that when the objects become electrically large and the mesh size becomes too much for computational resources, that's when you would like to apply the asymptotic solutions. First, let's take a physical optics approach. This is like normally, I call this as my one slide education on physical optics, where you have a infinite PEC surface, that is infinite ground, and there is an instant field, magnetic field, and that field is reflected, giving you reflected magnetic field. The current on this infinite ground is given by N cross H. That is, if you take the incident field and the reflected field, there is 2 N cross H, N being the normal to the surface. Of course, this is valid, very valid Maxwell's equation solution, but then we don't solve this infinite things. We solve finite things. But what people found back in the 60s and 70s when this method was very prominent because of the lack of computation sources is that you can apply this formula to even to finite structures and be able to get reasonably good answers because this approximation seemed to hold good when you apply to electrically large structures. So this is what we have to keep in mind when you apply physical optics. You're applying a exact solution of infinite ground to a finite structure. So if it is giving a good answers, that's always good. But if it's not as accurate, you have to keep this in mind that the reason why it's not giving accurate answers. So combining this with meta moments, for example, if you have a monopole or some complex antenna on your large surface, you can apply meta moments to this part and you can apply physical optics. See that this is electrically large, but also smooth. So physical optics works very nicely on this surface. And of course, meta moments can take care of any complex structures. Then you can solve the combined equation. So you take the coupling between these two regions as well, or these two methods. So for example, if you want to solve a reflector antenna with feed horn, you can apply meta moments to the feed, which is very complex, and apply physical optics to the reflector, which is very smooth and kind of, you go back to where physical optics came from. It kind of resembles that type of problem. So you compare that with MLFMM, very nice agreement, most of the radiation pattern region. Of course, now you take a little bit bigger problem, like this monochrome antenna on a ship with the sea surface here. You can solve this with at 500 megahertz. It's a large problem actually, maybe 3.5 million triangles. You could solve in 33 gigabytes and 1.1 hours. Of course, the reason I'm showing it is because I'll show you next our extension of this physical optics to what we call large element physical optics. This is actually done by when you have a smooth surface or a flat surface where you can have electrically larger triangles rather than lambda by 10, the one I was showing you earlier, and still be able to solve with the physical optics by incorporating a phase term into the basis functions that are being used. Now the same problem you can solve with LEPO, the large element physical optics on the reflector and method moments on the feed horn. You can see that the PO and large element PO gives you exactly the same answers in this case. Then you take the problem of this ship. Now you can see that instead of 33 gigabytes per physical optics, it is solved in 238 megabytes. This is even less than half a gigabyte, and 2.7 minutes compared to 1.1 hours. So it brings that advantage of using electrically larger triangles that can be used for discretization. And when you compare, obviously, they don't match exactly one or the other, but they come very close. So we're not saying that use LEPO for all the problems. We're saying when you don't have the memory, let's say you don't have 33 gigabytes, you could apply LEPO and get reasonable answers for your problem. Going a little bit further, we also introduced what's called iterative method moments and physical optics, or MLFMM physical optics. That is, instead of trying to couple the whole problem in one big solution, you can solve this separately and use those currents to radiate into physical optics region, and then use those currents back to radiation and back and forth till you converge, which also gives you very nice coupling between those two without having to spend extra memory for the coupling matrix. So you can see that all MLFMM method that is completely solving the whole problem, hybrid method that is taking the coupling matrix into account, iterative method, all three seem to agree quite well. Then let's go to the one more asymptotic method we have, ray launching geometrical optics, sometimes called shooting and bouncing ray method, which is very good for physical optics, is good for metallic structures. You can also apply that to dielectrics, but physical optics does not treat the transmission through the dielectrics very well. That's where ray launching geometrical optics comes into picture, where it can handle transmission through the dielectrics, but also reflection through the dielectrics as well as to the conducting surfaces very well. The only limitation RLGO is that because it launches the rays, you want to make sure that these rays are launched when they are very what we call the when they are very close to the surface. The rays could be grazing instants. That is, they're almost in the tangential or parallel to the surface. Then it could be very time consuming, and you may have to launch more rays. It may not be that accurate when you do that. So a good example for the ray launching geometry, again, coming back to the reflector antenna example here, as a case study, you can say you can take the feed horn and you can compute the radiation pattern and use the radiation pattern as a source for the reflector and use RLGO as your solution methodology for the reflector. So if I do this with the near fields, for example, if you start from the right, MLFMM with the horn feed, this is a complete solution, took 4.4 gigabytes, 7 minutes of the time. MLFMM with equivalent source, that is with the radiation pattern, 4 gigabytes, 3 minutes. And of course, with RLGO, the same with the equivalent source, 62 megabytes compared to 4 gigabytes. Of course, it takes a little bit 4 minutes compared to 3 minutes. That's because it has to launch the rays and takes a little bit more time. Again, here we're not saying jump on RLGO for every problem. Obviously, you want to start with this scenario. When you run out of memory, maybe you can try this one. When you run out of memory, you can go to RLGO or even physical optics and ray launching the LEPO for that solution. Of course, where RLGO shines is when you have a dielectric lens type of an antenna, and you can use an equivalent source and be able to compute. Again, this is not the solution we would like to apply when you are able to afford the memory and time. Only when you don't have the memory and time, you would like to apply. So 15 gigabytes reduced to 97 megabytes, 8 minutes to 11 seconds of solution. Last high asymptotic technique we have is uniform theory of diffraction. This actually does not work with the discretization. You make your object to be approximate your object with a flat plate, and then use diffraction theory, uniform theory of diffraction, where the reflections and diffractions and corner reflections, corner diffractions, and so on and so forth can happen. One advantage with this method is that once you have set up your problem, and with the computational cost does not increase with the memory, with the frequency. So you solve with 10 gigahertz, you could solve the same problem with 100 gigahertz with the same memory and time. That is because of the fact that the solutions that are done are almost like a closed form expressions for these diffraction coefficients, where the frequency term is already included in it. For example, if you take let's say, a cubical satellite, where you have a monopole in the middle here, and of course, all the surfaces can be approximate flat plates, and 6 gigahertz, it's not a big problem, so you can solve with MLFMM. You can also solve with UTD. You can see the good agreement between the green line, which is UTD, the blue line, which is UTD, and the red line, which is MLFMM there. Because one advantage is that this is also hybridized with metronome moment. So the monopole here is analyzed with metronome moments, and each of those segments become sources for UTD, and you can analyze the whole structure here. Now we can go to a bigger problem, 15 gigahertz. It's still at a 1 megabyte memory, and even at 6 gigahertz or 15 gigahertz, 1 megabyte. You can even go to 26 gigahertz or 30 gigahertz. It still will be 1 megabyte memory as it has taken for a smaller problem. So very quickly, I touch on antenna arrays. I won't talk much because we have talk coming up tomorrow. Of course, arrays can be analyzed with periodic boundary conditions, where you take one element, you apply the periodic boundary conditions, so it will look as though it's an infinite array, and you can, of course, use the element pattern to be able to compute the array patterns as well as the beam scanning, etc. We also have a method called DGFM. This is the domain Green's function method, which is actually published in 2014 by one of the authors of this code in FEKO, Daniel Ladek, who joined us, and now he works at University of Stellenbosch as a professor there. This is actually, you can take a similar type of elements, and you can compress this matrix to be a diagonal matrix, your impedance matrix. So you're only solving the diagonal matrix rather than solving the whole matrix of the array. The only constraint is that each element has to be identical to each other in geometry. Then it becomes, this approximation holds good. With that, you can do linear arrays, you can do any type of arrays, because these location of the elements is not an issue. They don't even need to be periodically placed. That means they can be aperiodically placed, and it can be solved. A little bit more advanced topics. Again, I won't take too much time here because already we're running out of time. Characteristic mode analysis that has become very, very important in antenna designs nowadays. Essentially, you can use this CMA analysis to find the modes of any structure without exciting it. They're the natural modes, natural electromagnetic modes of that structure. So that can give you the insight into the physics of the structure. So using that physics, you should be able to excite it properly, create an antenna out of it. Any arbitrary structure, it doesn't need to be any particular structure. That's what we call putting physics back into simulations. We published a paper in 2015 in IEEE Antennas and Propagation magazine. I would highly recommend that you read that paper to understand the methodology and how it can be applied to various applications. Then the machine learning for antenna design and optimization. As you can see here from the code, This has been around since 1959. It's just that we are now discovering its value because of the computational power that we have now. Machine learning is a family of algorithms that help make predictions from data sets. So how do we generate the data sets? In our case, we generate the data set using various simulations. And from there, we apply the regression with machine learning with regression to be able to compute a mathematical function that would replace these physical structure with a mathematical function. So when you do the simulations, you don't apply this physics-based simulation, but you apply this mathematical function for your simulation. So to create that mathematical function, you need a data set of simulations that need to be done. And once the mathematical model is there, you can actually even have a scroll bars and then see how your final response varies when you change the dimensions, for example, for a patch antenna like this. And then, of course, you can use that for machine learning, this machine learning model for optimization. So your optimization now doesn't take any time at all. It can be very, very fast. We have a tool called HyperStudy in Altair that can actually take care of how much data you need to generate for your machine learning model, and also create a machine learning model for you, and of course, optimize the model within HyperStudy. We actually offered a short course on this, and it's available at altairuniversity.com. If you Google it and you go to this link, myself and one of my colleagues here, Gopinath Gampala, it's actually a 3-hour short course. So half of it is about how the machine learning works and how you apply this in electromagnetic simulations. And the rest of the half is with the live demos between FEKO and HyperStudy. Going to my last topic here on education, Altair offers free FEKO student edition that can be downloaded from our Altair University website. Then we also offer a free ebook on FEKO. This is actually a PDF copy with little introduction to basics of electromagnetic simulation, but at the same time, it has got examples where you click on the example, you'll go to a video with a step-by-step demonstration of the example problem. So it's a good tool for learning FEKO without having to attend a training class. Then, of course, as mentioned in the introduction, I co-authored a book with Professor Atefel Sherbani and Payam Nairi at Colorado School of Mines. This is an antenna book. This is not a FEKO book, but it's an antenna book, but introducing antenna concepts through FEKO simulation. So this may be very useful in the early on when students normally don't get that much excited about equations. Maybe one can introduce antennas through the simulations. Once they get more interested, maybe you can introduce mathematics to the students so they can understand the physics better. Of course, if you are more interested in learning about the methodologies, simulation methods, one of the excellent books that are written early on was by Professor David Davidson on computational electromagnetics for RF and microengineering. This is actually the one where it's not for people who want to write a code or write the software. This is for the people who are using the software to understand how the methods work, like this presentation, for example. Also, I wrote a chapter along with Professor Sertel at Ohio State University in the Handbook of Reflector Antennas by Dr. Sudhakar Rao and Professor Shafai and Dr. Sharma, a chapter on numerical methods. If you have that book, that also gives you a short introduction. With that, I would like to thank you all for your attention. Of course, I can be reached at my email address, cjreddy@altair.com. And also my counterpart in India, Manoj Mangharjani, who is based in Bangalore, or Pune office, I guess, can help as well if you need any help. With that, thank you all for your time.
Thank you very much, Dr. C.J. Reddy, sir, for your detailed information on how computational electromagnetic techniques could be used for different applications. Thank you very much. And I also thank Manoj, sir, for getting the help in conducting the sessions. Now we have a couple of questions, sir. I'll just read it out for you. The first question is is the discretization error optimized in FEKO?
Yes, yeah. So we have right now what we have is that you can ask for a discretization error. So it will give you what are the errors. And once you have it, you can say, I want to rediscretize based on the error. So it will rediscretize it. But we are working right now to make it more automatic. So you can say discretize till the error is minimized. What we can call this as an adaptive meshing, which will come very soon in FEKO.
Okay, thank you, sir. Next question is for designing microwave integrated circuit components, will transmission line approach alone sufficient, or any other method would you suggest?
What I'm understanding from the question is that when you say transmission line approach, you use the transmission line equations to analyze that structure, which I think can work up to some point, as long as those transmission line equations can take into account what sometimes we can call as the coupling effects and the fringe field effects into account. But I think with the density of those circuits increasing, I would strongly recommend that, for those kind of things, you use the 3D simulation tools, which will take all the effects into account. Obviously, this is also where possible, right? Where it's the memory and the time of the computer also is a factor there.
Yeah, thank you, sir. Next one is when you say electrically large, is it lambda by 10 or lambda into 10? Is it?
So the discretization is always lambda by 10. That is, you can think of it as 10 points per wavelength, meaning if you have a sinusoidal wave, and let's say that's an analytical expression, right? Sine of something, and you want to discretize it, and you want to represent this by discretization. So how many points you want to put on the sinusoidal wave to be able to represent it accurately? If you put 2 points, obviously you won't be able to represent it. If you put 3, 4, 5, maybe 6, 7, you start to see a shape. But 10 is an optimum one where you can say that this is good enough approximation. So that's the discretization size one. But when we say electrically large structures, by that normally we mean, let's say if it becomes 5 wavelengths, 10 wavelengths, and 100 wavelengths, then it becomes electrically large. But of course, this definition of electrically large can also be taken in terms of, in the past, in the past, when the computational resources are not available that much, we used to say 10 wavelengths is big enough so you can go to pure physical optics. But nowadays, with the computers we have, 10 wavelengths is nothing. You can solve that with meta moments in no time. So now that what is electrically large, where you need to switch from full wave solution to asymptotic solutions, keep moving to higher and higher frequencies. Hope that answers the question.
Thank you. One more question is in FEM MOM require volume meshing unlike surface meshing in MOM. I guess the question is not clear to me. I don't know.
I think what question may be asking, I guess, is there's an FEM MOM hybrid method. You apply FEM in the volume and you truncate the volume with a meta moments mesh. So you don't actually have to have an air box around it. Typically, when you put an air box can't be very close to the antenna. It has to be slightly away from the antenna. Typically, people recommend maybe half a wavelength away from the antenna, or even more. And that also depends on what type of antenna you're analyzing. And this is like you're building a anechoic chamber, how far your absorber should be from your article of test, right? It's a similar analogy here in simulations. You can think of your absorbing boundary condition as the absorbers of your anechoic chamber. So you have to create a quiet zone in a way, I guess, for the antenna simulation. I mean, there's no numerical noise in your calculations. So that's one of the drawbacks of applying this air box. So what meta moments hybrid method will do, FEM hybrid method will do, is remove that unknown, meaning meta moments applies the free space Green's function that accurately implements the radiation boundary condition. So you can be on the surface itself, the meta moments mesh, and don't have to worry about any numerical noise. And of course, you can be a little bit farther away as well.
Yeah, thank you, sir.
That answer.
Yeah. Next question is, does the software prompt the method to be used for solving? That means which optimization method is better for which structure?
Yeah, which simulation method may be better for the structure?
Correct.
Yeah. Because that would be, a bit longer way, because as I mentioned before, application of the method depends on your computation resources, right? And also, you don't want to keep, brute force apply physical optics or relaunching up where they are not applicable. So it is still falls on the user to decide which method. So where possible, FEKO prompts, okay, you're applying method moments is too expensive for this system and we don't have memory, you can switch to MOM, MLFMM, or you apply MLFMM to a problem where it's not electrically large, FEKO will prompt you that you need to apply method moments. But switching between full wave solution and asymptotic solution is the decision that we leave it to the customer, because you don't want to lose the accuracy of full wave solution where you can afford it. At the same time, you don't want to lose the ability to do the simulation when you don't have the memory. So that's why, educating the customer or the user to know what to apply when is a very, very critical, I guess, so that they can use the software more productively.
Yeah, thank you, sir. Next question is machine learning algorithm can be applied for RF circuit design such as power amplifiers, LNA, etc.? Is FEKO helps in designing?
When FEKO is a what we call not a RF circuit design software, it's more of a 3D simulation tool for passive structures. So if you have active elements, we don't simulate that in FEKO. But in general, the machine learning can be used for any type of things. If you have a simulation tool available, our hyperstudy tool can interface with that and do the machine learning. But FEKO itself cannot do the active elements.
Yeah, thank you, sir. Next, last question we'll take is FEM MOM same as FEM BI?
Yes, yeah. So the other name they use is boundary integral method, which is similar to MOM. Sometimes they also call boundary element method in mechanical side, I guess they call BEM, boundary element method. Of course, in electromagnetics, one can use boundary integral method because they are truncating the boundary with the integral equation. And sometimes they also call IE integral equation method, FEM IE method. So we use as a traditionally method moments, which is coined, I guess, back in old days by Professor Harrington, I suppose, R.F. Harrington at the Syracuse University. So they're all, synonymous. Yeah.
Okay, sir. One more last question, sir. Sorry to.
No problem.
Yeah, when we have metallic plates inside a dielectric, which method would be appropriate for simulation? I think one student asked this.
Sure. No. Yeah, you can apply method moments for both because what we call surface equivalence principle is applied when there's only one single dielectric or maybe a couple of dielectrics, and you can apply method moments to it, but also you can apply FEM to it. It should be, so that's one thing we always are happy with the FEKO is that because we have both methods available, sometimes it's good to do both ways and see how well they agree with each other. That way you're confident about your own simulation as well.
Yeah, thank you, sir. Next, I request Chandrakant sir, any comments from your side?
Thank you, Dr. Reddy, for your nice introduction to the workshop and to be precise to different simulation methodologies that is being applied in electromagnetics, and that should be useful for the students. And as I told in the beginning that I must thank you especially because whenever I reach to you, no time you said no. And in that pretext, another interesting thing I picked up from today, from your biodata that was read out by Kirti today, that you are also very closely associated with the fellow elevation, that program. So from the Bangalore section as well as for APMTT, we want to hear you about some of the things. we have a program like FINE, Fellow Identification and Nomination Exercise. So I'll personally write to you for your time, and maybe that is one of the immediate engagement I can see I have to have with you. And thank you for your time today.
Yeah, Chandrakant, on the topic, one of the reasons why I agreed to that position was to understand what happens behind the scenes, right? Sometimes there are a lot of misconceptions about fellow program. Even I had those misconceptions before I became fellow, things will happen this way, so I should do this and this and this. And now I'm learning that, of course, it's all written and it's all in, long manuals that, IEEE put out on what happens in a fellow elevation process and those kind of things. But it is not, people don't read everything, right? People just go by what others say and others think of it, and what worked for them, what did not work for them. So I am actually learning a lot of things that could be very useful. And I plan to put together some kind of a presentation. Obviously, I need to go through the fellows committee to get approval that, what I say is accurate and I can say that to the public, right? Once I do that, I plan to do some kind of presentations, but also I might write an article. There's already an excellent article in IEEE APS magazine back in maybe 2016, I guess. I can send you if you want, I guess, if you don't refer to that before, written by, at that time, IEEE APS Fellows Committee chairs, Randy Hupt and Andy from the Georgia Tech University. That actually helped me a lot when I was preparing my own nomination or helping my nomination with the nominator. But that also leaves some other things, and now I'm at a higher level with the IEEE committee, right? You see different things than at the society level. I would like to definitely put together something that's in my plans for the future. I will let you know, and of course, we can communicate, I guess, on that.
Yes, sir. Our intention was to learn from the horse's mouth. That is, you can understand, because many of us we are very much scared of all these applications and all. So we're definitely looking forward to your this one. Whenever you are ready, I'll just keep on communicating with you. I'll just try to arrange it, and it will be from the section level, so it will be a very big event that I can assure. And thank you once again, sir, for your time. And Mahesh, you can formally.
Yes, sir. Thank you. Yeah. Thank you very much, Dr. Reddy, sir. On behalf of IEEE Bangalore section as well as APMTT Joint Chapter Bangalore section, we would like to thank you, sir, for your time and nice presentation. It would really help the students as well as the researchers who are working in the domain. And since Manoj sir is in contact, we can get, he was mentioning that some free demos software is available for students to use, at least the starting antenna projects. So it is really nice, and we thank you wholeheartedly for your support and your time, sir. Thank you very much.
I like to thank everyone for attending as well. Hope they can attend the rest of the talks as well and be able to benefit from them. Thank you all.
Yeah, thank you, sir. Thank you very much.
Bye. Bye.
Thank you. Thank you very much. Bye.